Last lesson is multiplying and dividing radical expressions. I'm going to do it as one video, but you're going to get it in class as two separate lessons. The first is multiplication, and the second is division, because division is its own kind of quirky thing. So multiplication. The square root of 3 times the square root of 6 is the square root of 3 times 6. That's the square root of 18. Does 18 hide any perfect squares in it? Do you know any statements that multiply to make 18 that involve a perfect square number? You do. It's 9 times 2. The 9 gets to come out as a 3. The 2 is left behind. So multiplying to get a single expression underneath a radical, and then simplifying as we have been. 5 root 3, quantity squared. Now this is multiplication, 5 times root 3, with an exponent outside of the multiplication. The rule for this, back with exponents, was to give the exponent to both of the things being multiplied, which means the 5 gets the exponent, and the root 3 gets the exponent. 5 squared is 25. Root 3 squared is 3. Remember, the square root of something squared. Square root and square cancel each other out. 25 times 3 is 75. We can combine the two multiplied square roots into a single square root by multiplying the radicands. 8 times 4 is 32. X times x is x squared. 32 is 16 times 2. And then your perfect squares come out. The square root of 16 is 4. 4 times 2 in front is 8. The x squared, its square root is x. And that 2 was the only not perfect thing still underneath the radical. It's left behind. Distribution is still a thing that happens. So when we multiply the root 2 here, we're going to get 5 root 2 plus root 24. 24. The best fact we can use to make 24 is 4 times 6. Yes, there are other facts that make 24, but the only one that involves a perfect square is 4. The 4 comes out as 2, the 6 is left behind. We can't actually combine these into a single term, and that's fine. We saw that happen in the previous notes. But we have distributed the root 2 and simplified everything we obtained. Distribute. Root 3 times root 3 is root 9, minus root 3 times root 5 is root 15. 9 is perfect. The square root of 9 is 3. And the only multiplication fact that makes 15 is 3 times 5. Neither one of those is perfect, so it's stuck. And hey, been a while since we foiled, but we're going to do it again. First times first, 4 times 3 is 12. Outer, 4 times negative root 5 is negative 4 root 5. Inner, root 5 times 3, both positive, is positive 3 root 5. Convention is always to write a radical expression with a radical as the second part, so even though we're saying root 5 times 3 written out, it's going to be 3 root 5. And then positive root 5 times negative root 5 is negative root 25. Positive times negative is negative, and 5 times 5 is 25. So let's look at what we can do here. We can combine the 2 root 5 things, so 4 root 5 plus 3 root 5, negative 4 root 5 plus 3 root 5 is negative 1 root 5, or just negative root 5. that last term, though, root 25, is 5. Which means we again have like terms, 12 and 5, the two numbers that are free of square roots. 12 minus 5 is 7, and the minus root 5 is still minus root 5. So that's multiplication. Division is actually its own special thing called rationalizing the denominator. Remember, one of the rules for radicals was no square roots in the denominator of a fraction. And if there is one, so far we've been lucky. We've either had it be a perfect square, or we could simplify the fraction so that it would become a perfect square. And that's not the case with these guys. So what the heck are we going to do? Well, the simplest thing for me to tell you is say, hey, you have a square root in the denominator, and I'm saying you're not allowed to. Let's multiply the numerator and the denominator by the square root in the denominator. So in this first expression, that's root 2. Both top and bottom get multiplied by root 2. If you look, what are we doing? We're multiplying by something over itself. Now, we've made an odd-looking something over itself, but we're secretly multiplying by 1. We're just changing how it looks. Okay, this is very similar to simplifying a fraction. We're just changing how it looks. So in the numerator, root 7 times root 2 is root 14. In the denominator, root 2 times root 2, by design, is 2. Why is that true? Root 2 times root 2 is root 4. Root 4 is 2. We have ourselves a fraction. There's no square root in the denominator. There is a square root here, so we do need to stop for a second and say 14, 14, 14. The only way I can make you is 2 times 7, and neither one of those is perfect. Root 14 over 2 is as good as that's going to get. Now, in the last example we have here, we have root 7 over root 8n. We could just straight away say, okay, we're going to multiply the numerator and the denominator by root 8n. Because this will work. In the numerator, root 7 times root 8n is root 56n. In the denominator, root 8n times root 8n is 8n. And again, why is that true? Well, root 8n times root 8n is root 64n squared, and root 64n squared is 8n. We're not done here, because 56 is hiding something from us. 56 is hiding a perfect square. Which one? Four. 4 times 14 is 56. Which means the 4 itself can come out of the radical. Now, you might think we're done, and we are very close, but we're not done. We have parts of this final expression that are outside of square roots, 2 and 8n, and parts that are inside square roots, root 14n. While it is true that things underneath square roots cannot simplify with things that are not underneath square roots, things that are completely clear of radicals are allowed to simplify. And specifically here we're looking at the 2 and the 8, which become a 1 and a 4 respectively. So what does that mean for our final answer? Well, I'm not going to write the 1 because 1 root 14n is just root 14n. The denominator, the 8 became a 4. I can't ignore 4. Our denominator is 4n.